Dear students, today I explain how to solve problems which we discuss on chemistry practice number 4. These problems are divided into two groups. The first group is about properties of solutions of weak electrolytes. The second group is about osmosis phenomena. So please stop the video and write the question, write the problem, and I will show how to solve it. First of all, you have to start with the writing of dissociation equation. Acetic acid, as other organic acids, is a weak electrolyte. So for weak electrolytes, we write the dissociation the following way CH3COOH. When we write two arrows, the arrows should be in two directions. It means that there is an equilibrium. Acetate ion, acetate ion and proton. So let me remind you what is alpha. Alpha, it is degree of ionization or degree of dissociation, which shows us the ratio of substances dissociated to a total number of substances. So we can write also alpha using molar concentrations. This ratio I showed you on lecture number 2. So above we write the molar concentration of protons, or we can write molar concentration of acetate ion. It's the same. These two concentrations are the same. And below we write the molar concentration of acetic acid. So actually the question is the molar concentration of acetic acid. So this we have to calculate. Yes. And we can transform this formula and write that the molar concentration of acetic acid is equal molar concentration of protons divided by alpha. So let's find the molar concentration of protons. How to find that? Let me remind you that pH is a negative logarithm of equilibrium concentration of protons, or in our case it will be the same as a negative logarithm of molar concentration of protons. So if we know that pH is equal 4, then we can conclude that molar concentration of protons is 10 power minus 4. So I will write here, we put numbers here, above I put 10 power minus 4, below I will put alpha, which is 1.3%, but to make it more correctly, we will not use percent, we'll use number 0.013. And if you do that calculations, you will find that the molar concentration of acetic acid is 0.0076, and units are mole per liter. Basically that's it. That's the solution. Problem number 2 You can stop the video and write the problem. So let's write the dissociation equation. Formic acid, HCOOH, 2 arrows, forming 8 plus proton. So let's read the question again. We have to find concentration of protons and pH, and the concentration of formic acid is not given, but we have number of moles of formic acid and volume of solution. So let's find the concentration of formic acid. We will divide number of moles by volume. So 2 multiplied 10 power minus 4 divided by 2. Here are moles, here are liters. So it will be 1 multiplied 10 power minus 4 moles per liter. Or you can don't write 1, just 10 power minus 4. So we use the same approach as we used on previous problem. Alpha is equal molar concentration of protons divided by molar concentration of acid. So we have to find that. So we write that molar concentration of protons is equal alpha multiply molar concentration of acid. Alpha is given, it's 0.01 multiply 10 power minus 4 moles per liter, and we will get 10 power minus 6 moles per liter. And the pH of that solution will be negative logarithm of molar concentration of protons, and actually it is 6. That's it. Please read and write down the next problem. You can stop the video. Okay, let's start with dissociation equation. Ammonia hydrate. It is NH3 multiply H2O, or you can write the following way, NH4OH. It is the same. So NH4OH dissociates, you write 2 arrows, and it gives us ammonia ion and hydroxide ion. So there is no alpha, but we see that there is given ionization constant. So what is the ionization constant? This I also explained on lecture number 2. It will be written through equilibrium concentrations. Equilibrium concentration we write in square brackets. So above there will be product of equilibrium concentrations of ammonia and equilibrium concentration of hydroxide ion, and below equilibrium concentration of ammonia hydrate. So actually these two equilibrium concentrations, they are the same, they are equal, because each molecule of ammonia hydrate produced one ammonia ion and one hydroxide ion. So we can write in that formula above the equilibrium concentration of hydroxide ion power 2, and below we can write not equilibrium concentration of ammonia hydrate but molar concentration, because in our case this is a weak electrolyte and the molar concentration is very close to equilibrium concentration. So now let's read attentively what we have. We have molar concentration of solution, it's given, and ionization constant is given. So we will write that equilibrium concentration, I will do step by step, power 2 is equal molar concentration of ammonia hydrate multiply ionization constant, and when we have to do some mathematics, so the equilibrium concentration of hydroxide ions will be square root of the product of that product. Now we put all the numbers. 0.001 multiply 1.75 multiply 10 minus 5, and it will give us 1.32 multiply 10 power minus 4 moles per liter. Actually, this is the answer to our question. In that case, molar concentration is the same as equilibrium concentration. Problem number 4. Please stop the video and write down the question. In that problem, we compare two solutions, the solution of strong and weak electrolytes. So if you read attentively, you will see that there is given degree of dissociation for nitric acid. So we can assume that nitric acid is a strong electrolyte, because strong electrolyte has high degree of dissociation, and acetic acid. Acetic acid has a small degree of dissociation. So we know for both solutions that pH is the same, but we have to find the molar concentration. First, let's start with strong electrolyte. For strong electrolyte, we draw one arrow. It fully dissociates. And for strong electrolyte, we can assume that the concentration of acid is equal to concentration of protons, and we can find it through pH. So we can assume that it will be 10 power minus 3, as pH is equal to 3 moles per liter, or I will write it this way, 0.001. Now let's find the concentration of acetic acid. Let's write the dissociation. We did it in first problem. CH3COOH, then two arrows, CH3COO minus plus H plus. And you have to find in your lecture notes the formula for calculation of pH of weak electrolytes. It looks the following way: pH is equal 1/2, when in roots there will be the sum of pKa plus Pc. So I remind you that pKa is a constant, Ka is constant, and pKa is a negative logarithm of ionization constant for acids. This small a means acid. Pc is a negative logarithm of molar concentration of acid. So we have to find the molar concentration, so we have to find that C. So let's transform the formula. Pc will be pH multiplied 2 minus pKa. So pH is 3 multiplied 2. pKa it's not given, but I will tell you from reference book it will be 475. So minus 475, and we find that it is 1.25, and the concentration, to find the concentration you have to take 10 power 10 power minus 1 to 5, and it is 0.056 moles per liter. This is for acetic acid. Please pay attention that in that problem we had two solutions. One solution of strong acid. This was strong acid here. Strong electrolyte, yes. And this one is a weak. So two solutions has the same pH. So two solutions, they have the same pH. Yes, solution number 1 and 2, pH 1 is equal to pH 2. But the concentrations are different. So you see that the concentration in weak electrolyte solution is 56 times higher than concentrations in strong electrolyte solution. So strong electrolyte, it's a diluted solution. Weak electrolyte is very, very concentrated, 56 times more concentrated. But they have the same pH because in strong electrolyte, molecules dissociate fully for 100%. But in weak electrolytes, molecules dissociate just in a very small percent, 1.3%. This is important. I hope you understand that difference. Now we will discuss problems about calculation of osmotic pressure. I remind you that generally we divide all solutions into two groups, non-electrolytes and electrolytes. The formulas for calculation of osmotic pressure are similar. So for non-electrolytes, osmotic pressure P is equal C multiply R multiply T. For electrolytes, we have small difference. It's I, small I. This is isotonic coefficient. multiply C, multiply R, multiply T. So please write down that question. You can stop the video. First of all, we have to understand if we have electrolyte or non-electrolyte here. Okay, we have electrolyte. It's potassium chloride. It is salt, and also we see that there is given isotonic coefficient. It's I. So we just write the formula P equal I multiply C multiply R multiply T. And then we'll put all the numbers. I remind you that R is a gas constant. It's equal 8.31 joules per mole per Kelvin. And in case if we use that number for gas constant, we will find osmotic pressure measured in kilopascals or pascals. So I write P equal 1.96, it's I, isotonic coefficient, multiply C. C is a molar concentration, it's given here, 0.01, multiply R, 8.31, multiply T. The temperature is given here, it's 310 kelvins. And if I do all that calculations, I will find that osmotic pressure is equal 50.5 kilopascals. The second question, is this solution iso, hyper or hypertonic in relation to the blood plasma? And there is given osmotic pressure for blood plasma. So we have to compare. This is osmotic pressure for potassium chloride. So we have to compare osmotic pressure of potassium chloride and osmotic pressure of blood plasma. And we see that it is smaller. The osmotic pressure of potassium chloride is smaller than osmotic pressure of blood plasma. In that case, we know from lecture number 2 that the solution will be hypertonic. Hypertonic. So the conclusion is that solution is hypertonic. Problem number 6, please stop the video and write it down. Basically, we see that this is a glucose solution. Glucose is non-electrolyte, so we will calculate the osmotic pressure using that formula. P is equal C multiply R multiply T. And the most difficult part of that problem is to find C, molar concentration. It's not given. We see that there is given mass fraction, omega. It is measured in percent. So, and it's equal 20%. So the question is how to convert one type of concentration to another. For that, we can use the following approach. We can fix the volume of solution. We can say, let's the volume of solution is equal 1 liter, or it is 1000 milliliters. We have density here. Density is given. So we can calculate this volume of solution. We can calculate the mass of solution. For that, we will multiply density and volume. So 1.08 multiply 1000 will get 1080 grams. This is the mass of solution, 180 grams. So you can open your notes from first practical lesson and find the formula for mass fraction. So it is mass of dissolved substance, in our case of glucose, divided by mass of solution. So we can calculate the mass of glucose as mass of solution, which we just calculated, multiply by omega. And we take 1080 grams and multiply it by 20%. And as we have to cut percent, we have to divide it here by 100% to cut the percent. Actually, here I will add multiply 100%. Here also. So if you do that calculation, you will find that the mass of glucose is 216 grams. This is the mass of glucose, 260 grams. To find the molar concentration, we have to find number of moles. So let's calculate number of moles. It is mass divided by molar mass. So 260 grams divided by molar mass. Molar mass of glucose is 180 grams per mole. And it will give us 1.2 moles. And so the molar concentration is equal 1.2 moles, and we have divided by volume. The volume is 1 liter. 1 liter. So 1.2 moles per liter with M. So now we will take basic formula and put all the numbers here. P is equal 1.2 multiply 8.31, this is gas constant, multiply 310, and it will give us 3091 kilopascals. The second question is whether this solution is hypertonic, isotonic, or hypotonic. So we see that it is it has higher osmotic pressure when blood, so the solution will be hypertonic.